We start with the basic M5 model using a transconduct element where like the output current is proportional to the voltage difference between two inputs, V2 and V1. We can see V2 and V1 at the image that I didn't include in this document. So the current generated will be we can use like E out, U out equal GM V2 minus V1. This current flows through the resistor R, generating a voltage across it, so it means this equation. So now we have to compute it for voltage V3, which means this voltage is basically passed through a second gain stage with gain micro mu, and it means this equation. Now we just compared these two equations with the general amplifier equation, and we got that A is equal 10,000, and we also can compute decibel value, which means 20 logarithms value of A equal 8 decibels. Question number 2. In an inverting amplifier, the closed loop gain is affected by both the feedback network and the gain of the operating amplifier. So we can see the open loop gain here, and we should express this term of R1 and R2. So the general gain formula when considering a finite open loop gain A is this one. This tells us that the gain is not just minus R1 over R2 over R1, but also depends on A. When A approach to infinite, the denominator approach to 1, and we get the ideal gain, which equals AV. So AV is equal minus R2 over R1. But if A is finite, the amplifier won't reach this ideal gain unless this equation. Also, this minimizes depends of G on the open loop gain A. Question number 3, input resistance with feedback. We're looking for the input resistance R in equal YE over IE seen by the source. Because of the virtual short and no input current, we analyze node 2 using KCL. Define Y minus equal minus 1 output over A. Now we can just apply KCL, and we can get these current balance equations. Now we just substitute we basically just substitute and solving for YE, and we can get this equation. From here, we just find input current IE and substitute, and we get a final and simplified version of our input resistance with feedback, which equals R2 plus R1 times 1 plus A over 1 plus A. If A go to the infinite, R1 equal R. Input resistance equal R1. With lower A, feedback reduce input resistance. Here we can see compute for two cases. One was 1989 ohms and the other was 1.1 kilo ohms. With modest gain, feedback reduced the input resistance significantly below R1. With large gain, input resistance becomes R1, consistent with idle operating amplifier behavior. Now we have to analyze how the source resistance Rs impacts the gain. Due to voltage divider between Rs and R1, the voltage entering the amplifier is equal to this equation. Then the amplifier process Yi and produce output voltage will be minus R2 over R1 plus R2 plus A times R1. All of these times we input voltage. Now we just divided this equation by input voltage and or just put it on the other side, and we can we have this equation. We can detonate this as some gain G, and overall gain GV will be basically the same, just with time with this also with this gain. So we can get rid of we just times by this gain, and final expression we can see here, and this expression shows how the source resistance Rs and the amplifier finite gain I affect the overall voltage gain. Non-inverting amplifier and voltage source. Question number 5. Non-inverting amplifier gain is simple. The input voltage appears at the positive terminal. Using voltage division at the negative terminal and the virtual shorts, we get this equation. If there's source resistor Rs, it doesn't matter because no current enters the operating amplifier, so V1 becomes voltage 1 becomes input voltage. We can just substitute this output voltage, and we get this equation, and the final expression for gain is shown here. So basically we just divided output voltage with the input voltage, and as we can see we can just scratch this formula, and this shows that for non-inverting amplifier the voltage gain is determined purely by the resistors ratio R1 and R2 and R1. Signal source model. The non-inverting input of the amplifier has infinite input impedance, so no current flows into the input, therefore there is no voltage drop across Rs, and the voltage at the non-inverting input is input voltage equals voltage S. In the ideal case, the input voltage equals the source voltage. That's the conclusion. We can have this equation from the question above, And so we just conclude that the overall voltage gains is the same. So the source resistor has no effect in the non-inverting case, which is a big advantage. This is an ideal case of non-inverting amplifier where the entire source voltage appears at the input of the OP amplifier, operating amplifier. Question number 7, voltage follower. This is just non-inverting amplifier with a R2 equals 0 and R1 usually should be close to infinite. The input signal is connected to the non-inverting input. The output is directly connected to the inverting input. No external resistor are required for setting gain. So behavior and characteristics: voltage gain is usually 1. Unity gain: input impedance, input resistance very high, close to infinite. Output impedance very low. It should be ideally 0. Feedback type 100%. Signal ratio: output is equal to input voltage. Practice implications: high input impedance doesn't load the source. Low output impedance can drive loads used as buffer. This is crucial when connecting a weak signal source to a heavy load, for example a sensor to an ADC. To isolate stage of circuit, to maintain signal integrity when interfacing different impedance levels, to improve power delivery to a load without alternating voltage. You can see one over here. Question number 8, difference amplifier. This circuit subtract to input. Using superposition, apply one y1 set v2 is equal to 0, behaves like an inverting amplifier. So the circuit reduced to an inverting amplifier with this equation. Apply y2, set y0, and the circuit becomes a non-inverting amplifier with a voltage divider at the input. Applying the gain of non-inverting amplifier. So to ensure the amplifier performs true subtraction, these must match. With that, the output should be equal here, and input resistance should be the total different input resistance is here. On this equation, we can also see that is Thevenin equivalent of the voltage divider formed by R3 and R4, which basically we can see here. And also a different voltage gain should be also depends only on of the two resistance. Peak rectifier. A peak detector holds the peak of a sinusoidal signal using a diode and a capacitor. When input voltage is larger than output voltage, the diode conducts and the capacitor charges the peak. When we switch this term, the diode turns off and the capacitor slowly discharges through the load resistance. Key condition we can see here. Also capacitance, resistance, uh, input signal period, and frequency. Ripple voltage. This shows that increasing C and R or F reduce ripple, and then current through the load and diode. So conclusion, bigger C means less ripple, diode conducts only briefly, capacitor holds charge, also used in envelope detectors, pig hole circuits. Question number 10. Join p-type holes and n-type electrons carries diffuse across the junction. Recombination leaves behind fixed ions, forms a depletion region. This creates electric field that opposes diffusion. Drift current develops in the opposite directions. At equilibrium, drift and diffusion currents cancel, which means net current equals to 0. Built-in potential is equal to this equation, where K is Boltzmann constant, T is absolute temperature, Q is the electronic charge, and Na and Nd are acceptor and donor doping concentrations, and Y is the carrier concentration. This internal voltage prevents further carrier movement, forming the diode-like behavior of the junction. And in here we can see also the picture, the formation of the p-junction.